In this video, we're going to look at how to find the arc length of a smooth curve, which is given by a function of y instead of a function of x. We already know that if we have a curve that is described by an equation y equal f of x, which is a function of x, and that curve is smooth between points corresponding to x equal a and x equal b, then we can compute the length of that curve, that portion of that curve, by computing the definite integral from a to b of the square root of 1 plus the derivative squared dx. Here we have two different integrals describing that quantity, only differing in the notation of our derivative. We have prime notation in the first integral and rate of change notation dy dx in the second, but otherwise these are exactly the same quantity. If instead we have a curve described by an equation x equals g of y, where y is now going to be the variable, and this curve is smooth between a point corresponding to y equals c and another point corresponding to y equal d, we can compute the length of that portion of that curve by computing the definite integral from c to d of the square root of 1 plus the derivative of y squared. We can represent the derivative of g in two different ways. We can think of it in prime notation using g prime of y, or we can think of it in rate of change notation and have the expression dx over dy. Again, these are both the same integral, just using different derivative notations. It's important to notice that these two different arc length formulas for functions of x and for functions of y, respectively, are nearly identical, except for one deals with a function of x and the other with a function of y. This is extremely helpful when we go to actually compute arc lengths of functions, because we don't really have anything new to do if we have a function of y. We just have to express all of our values and all of our functions along the way in terms of y instead of in terms of x. This formula here is easily verified much the same way as it is for functions of x, just simply by reversing the roles of x and y throughout the entire verification process. So let's look at an example where we want to find the length of the curve given by x equals natural log of cosine y along the closed interval from 0 to pi over 3. In the notation that we just used, natural log of cosine of y is going to be the formula for our function g of y. And so we'd like to compute this arc length by finding the square root of 1 plus the derivative of g squared, and then evaluating that integral from the integral of that from 0 to pi over 3. So here we go through the same algebraic steps as we would if this were a function of x. We first compute the derivative of our function g of y, so we want g prime of y. This is a composition, so we need to use the chain rule. So the chain rule here will be 1 over the cosine of y, that's the derivative of the natural log function. But then we do need to remember to multiply by the derivative of cosine y, which we know is negative sine y. And so this here, this multiplication here is in fact an instance of the chain rule. So we have 1 over cosine times negative sine, and this can be rewritten if we want as negative sine of y over cosine of y, or more simply as the negative of the tangent of y. And this will be helpful when we go to square it here in just a moment. Once we have g prime of y, we want to take that derivative and square it. And so we want negative tangent y quantity squared, and that ends up being just tangent squared of y. We then want to add 1 to that expression. And so we're simply going to have 1 plus tangent squared y. And recalling a fundamental trigonometric identity, 1 plus tangent squared of y is going to always equal the secant squared of y. And so in our last step to compute our integrand, we want to take the square root of 1 plus g prime of y quantity squared. So we want the square root of secant squared of y, which is just the secant of y. And so for this particular function, we actually get a very nice integrand that we're going to be able to integrate over, and we're going to integrate the function of secant y. So now that we have that particular integrand, we're going to find our arc length by integrating from 0 to pi over 3, our integral of that we care about, of the secant function, secant y dy. Recall that we know an antiderivative for secant of y. It's going to be the natural log of the absolute value of secant y plus tangent y. And we're going to evaluate that expression from 0 to pi over 3. When we substitute pi over 3 into this equation, we're going to get the natural log of secant of pi over 3 plus tangent of pi over 3 minus the natural log of secant of 0 plus tangent of 0. And now we just evaluate these trig functions appropriately. Secant of pi over 3 is going to be 1 over the cosine of pi over 3, so 1 over 1/2, which is 2. And tangent of pi over 3 is the sine of pi over 3 over cosine of pi over 3, and we can check quickly that that is going to be the square root of 3. In our second term here, we have the secant of 0, which is 1 over the cosine of 0, which is 1 over 1, or 1. And tangent of 0 is 0. And so our second term here, we have the natural log of 1, which we know will be 0. And so the length of our curve on our appropriate interval is simply the natural log of 2 plus square root of 3. And here, if we want, we can actually leave off those absolute value bars because 2 plus square root of 3 is, in fact, a positive number. And so the absolute value does not change anything. And so here is the arc length of our function from 0 to pi over 3. If you'd like to try a similar example, find the length of the curve given by the equation x equals natural log of secant of y along the interval 0 to pi over 4. Resume the video and see the full solution in a few seconds. We first need to find the expression, the square root of 1 plus the derivative squared. So we first find the derivative of our curve, which will again be computed using the chain rule. Here we have 1 over secant of y multiplied by the derivative of secant y, which will be secant of y tangent of y. And the secants here will cancel, and we're left with just the tangent of y. We then square that to get tangent squared of y. Add 1 to get 1 plus tangent squared y, which is the same as secant squared of y. And then take the square root, and since we have the square root of a perfect square, we're left with just the secant of y as our integrand. Since we want the length of the curve from y equals 0 to y equal pi over 4, the length will be given by the definite integral from 0 to pi over 4 of secant of y dy. An antiderivative for secant of y will be the natural log of the absolute value of secant y plus tangent y, and we evaluate that from 0 to pi over 4. When we substitute pi over 4 and 0 in for y into our expression and realize that the natural log of 1 is equal to 0, we end up with a final value of the natural log of the absolute value of 2 over square root 2 plus 1. And like in the previous example, the absolute value bars can be dropped here since we're taking the absolute value of a positive number.